China's liquid metal breakthrough is about to change robotics forever, and almost nobody outside a handful of labs knows it exists yet. While American and European robotics companies race to build stronger motors and lighter joints, researchers in Beijing quietly built something that needs no joints at all. You heard that right. A machine that changes shape instead of relying on hinges, gears, or fixed limbs. Picture a wrench reshaping itself into a screwdriver, then back again, in seconds. And that is just the beginning, because the real competition is not over who builds the better robot. It is over who controls the material every future robot might be built from. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you will understand exactly why the robotics industry is watching this material. But first, see what the rest of the world is still building without it. For 70 years, robotics has been built on one simple idea, and it has earned every bit of its dominance. A robot is a collection of rigid parts, joined by hinges, driven by motors, and controlled by gears that translate electricity into precise, repeatable motion. This is not an accident of history. It is the result of decades of engineering that made rigid robotics the only reliable way to build a machine that does the same task the same way, 10,000 times in a row, without ever drifting off course. Engineers love this approach because a motor and a gear behave the same way every single time you ask them to. Manufacturers love it because rigid parts can be mass-produced on the same assembly lines that already build cars and appliances, keeping costs predictable. Governments love it because rigid motor-driven robots are already certified, already insured, and already trusted inside factories that cannot afford a single unplanned failure. Picture a socket wrench. It only works because it holds one exact shape every time you pick it up. That predictability is the entire foundation of modern automation, from a car factory in Stuttgart to a warehouse outside Shenzhen. So why didn't anyone solve the obvious problem with this approach sooner? Because for most of robotics history, nobody needed to. Rigid machines could lift 11,000 pounds, the weight of a loaded delivery truck, without breaking a sweat, and that strength made every other limitation feel like an acceptable trade-off. Here is the part that most people never stop to consider. Every one of those rigid joints is also a fixed liability, a point that cannot bend, cannot squeeze, and cannot adapt to a space it was not built for. A rigid robotic arm cannot slip through a gap 2 inches wide. It cannot reroute around a broken joint mid-task. It cannot change its own shape to fit a problem nobody anticipated when it rolled off the factory floor. That rigidity is not a flaw in the design. It is the design. Every strength the system offers comes bundled with the exact same weakness, baked into the same steel and the same motors. And that raises a question engineers have quietly avoided for decades. What happens when the task itself refuses to hold still? That question would not stay buried forever. But the answer would not come from a bigger motor, a stronger joint, or a smarter gear. It would come from a material that refused to follow the rules. Rigid robotics was built on entirely. Underneath all that reliability sits a structural flaw that rigid robotics can never engineer away because it is not a manufacturing defect. It is a geometric one. A rigid machine has one shape permanently, and a permanent shape is a permanent set of limits on where that machine can go and what it can survive. This is not about robots occasionally getting stuck. It is about an entire category of tasks that rigid machines were mathematically incapable of performing from the very beginning. Consider the numbers. Roughly 80% of search and rescue environments, collapsed buildings, flooded tunnels, and pipeline interiors contain gaps narrower than 6 inches, about the width of a standard notebook. A rigid robot built to lift 11,000 pounds cannot pass through a gap the width of a notebook, no matter how advanced its motors are. Here is the brutal catch. The industries that need robots most, in disaster response, deep pipeline inspection, minimally invasive surgery, are precisely the industries where rigid geometry fails first. When a rigid inspection robot cannot fit through a damaged pipe joint, the entire pipeline goes offline for manual inspection, sometimes for weeks, at a cost that can run past $200,000, roughly the price of 6 new delivery vehicles, for a single shutdown. The consequence ripples outward. Insurance premiums climb. Infrastructure inspections get delayed. Surgeons are left choosing between a larger incision or a procedure a rigid tool simply cannot perform. This is not a minor inconvenience tucked into a spec sheet. It is a hard ceiling on what automation can reach, no matter how much money gets poured into better motors. Most people assume the fix is a smaller robot, a thinner arm, a more flexible hinge. But a smaller rigid machine still has a fixed shape. It just has a smaller fixed shape. The limitation does not disappear. It only shrinks alongside the robot. What if the shape itself were not fixed at all? What if a machine could be solid enough to do real work, hold a tool, grip a ledge, carry a load, and liquid enough to become something else entirely, seconds later, without a single motor turning? In 2024, researchers in China began answering that question with data that was harder to dismiss than anything the field had seen before. And once you see what they built, you will understand why every rigid robot on Earth suddenly looks a little bit outdated. The team behind this breakthrough works out of Tsinghua University in Beijing, alongside collaborators at the Chinese Academy of Sciences. And their approach did not start with a bigger idea about robotics. It started with a smaller idea about a single metal that most engineers had spent decades ignoring. The core idea sounds almost too simple once you hear it. Gallium, a soft metal alloyed with indium, melts at roughly 86 degrees Fahrenheit, colder than a warm bath. Mixed correctly, it stays liquid at room temperature indefinitely, behaving like mercury, but without the toxicity that made mercury unusable for this kind of work. Earlier attempts to use liquid metal in robotics failed for one specific reason. Once the metal became liquid, it stayed liquid, with no way to solidify back into a shape strong enough to grip or hold weight. A liquid that never hardens again is not a robot. It is a puddle with good branding. Here is the detail that puts everything into perspective. The Tsinghua team solved this by embedding the liquid gallium with microscopic magnetic particles, then using a targeted electric charge or a controlled magnetic field to trigger the metal between its liquid and solid states on command in under a second. Picture an ice cube tray that can freeze and thaw itself instantly, exactly where and when you need it to. What changed was control, not just material. Previous liquid metal experiments could reshape metal, but they could not decide, precisely and repeatedly, when solid became liquid and when liquid became solid again. The magnetic particle embedding gave researchers a switch, not just a substance. That switch is what turned an interesting chemistry demonstration into an actual engineering platform. Early demonstrations showed the material squeezing through a gap the width of a house key, then resolidifying into a shape strong enough to pull weight. A rigid robot could never survive that gap. This one flowed through it like water, finding its way downhill. This is not the first attempt to tame liquid metal. Researchers at the University of Sussex and Swansea University demonstrated basic electric charge reshaping back in 2017, and a joint American and Chinese team later shrank a liquid metal figure down to 10 millimeters, small enough to slip between the bars of a miniature mock jail cell. Those experiments proved the concept could work in principle. They did not prove it could carry weight or survive outside a lab bench. The chemistry itself was elegant, but elegant chemistry has fooled research labs before, with headlines that quietly faded once nobody could replicate the result at scale. The real question was whether this specific material could perform under real load, consistently enough to matter. Here is the honest number first. In its current form, This liquid metal material can hold a load of roughly 2 pounds per square inch once solidified, a fraction of what a rigid steel joint can bear, which routinely handles loads 100 times greater without strain. But here is what that number actually means in practice. Most tasks where shape-shifting robotics actually matter, threading through rubble, navigating a collapsed pipeline, moving through the human body, do not require lifting heavy loads. They require squeezing through spaces nothing rigid can reach at all. A search and rescue sensor package weighs a few ounces, not a few hundred pounds, and 2 pounds per square inch is more than enough to carry it through a gap 6 inches wide. Now, here is the part that flips the whole comparison. In one dimension, this material already beats rigid robotics outright. Recovery. A rigid robotic arm that gets crushed or bent in a collapse is finished. This material, once damaged, can simply be melted, reformed, and resolidified into its original shape in under a minute, with no replacement part and no factory return. There is a non-obvious application already benefiting today, one nobody expected 5 years ago: minimally invasive surgery. A liquid metal probe can travel through a passage narrower than a coffee stirrer, then solidify at the target site to apply steady, controlled pressure, something a rigid surgical tool physically cannot do without a larger incision. Earlier medical research already used liquid metal for angiography and vascular imaging, so the biocompatibility groundwork was largely in place before robotics researchers ever entered the picture. That head start is part of why adoption in medicine is moving faster than adoption in heavy industry. Here is what most people get wrong about this material. They assume liquid metal robot means a weaker, gimmick version of a real robot. It is not weaker in the category that matters most for the tasks it is built for. It is differently strong, built for geometry rather than raw force, the same way a rope beats a steel bar at wrapping around something irregular, even though the bar wins every contest of straight-line strength. The question was no longer whether liquid metal robotics worked. The question was, who would be the first to move it out of the lab and into a real disaster site, a real hospital, or a real factory floor? That question, it turns out, already has an answer. In 2024, at a Tsinghua University robotics lab in Beijing, researchers demonstrated a wheeled robot whose entire motion came from shifting droplets of gallium-based liquid metal inside a sealed tube, changing the machine's center of gravity with nothing but a controlled voltage. No motor turned, no gear engaged. The wheel rolled anyway, redirected across a flat surface purely by where the liquid metal chose to pool. The field matched the forecast. Lab predictions about how the voltage would redirect the metal held up under repeated testing, run after run, rather than collapsing the moment conditions shifted outside a controlled bench setup. Field validation matters more in this industry than almost any other, because a robotics concept that only works under laboratory lighting and laboratory temperature is not a robotics concept the world can actually deploy. A pipeline in rural Guizhou does not care what happened in a climate-controlled lab in Beijing, and neither does a collapsed building in an earthquake zone where dust, moisture, and temperature swings punish any material that only performs well on a clean workbench. One detail lowered the barrier to adoption significantly. The gallium-indium alloy at the heart of the system is compatible with existing microfabrication equipment already used to produce flexible circuits and wearable electronics, meaning manufacturers do not need an entirely new factory, an entirely new supply chain, or years of retooling to begin producing components. Researchers have also published their methodology through open-access engineering journals, including detailed reviews on liquid metal sensors for soft robots, letting independent labs outside China attempt to replicate the results rather than take the claims on faith alone. Next, we intend to use multiple wheels to move it in a three-dimensional environment. One of the lead researchers on the project explained, describing the team's plan to scale a single moving droplet into a coordinated, multi-limbed system. If a machine with no motor just moved itself using nothing but liquid metal and a voltage, The next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. It started with one wheel, where cost and simplicity mattered more than raw lifting power. Then it spread outward from there, into multi-pixel magnetic soft robots built from silicon and liquid gallium that can be reconfigured, pixel by pixel, for entirely different tasks. The claim now had receipts. That receipt did not stay inside China's borders for long. More than 400 international patent families now cite gallium-based liquid metal actuation for robotics and flexible electronics, filed across China, the United States, South Korea, and the European Union. These are not academic citations. These are legal and financial commitments, the kind companies only make when they believe a technology is heading toward commercial products, not just conference posters. Several organizations have already moved from interest to action. The Chinese Academy of Sciences has continued funding follow-on research into magnetically reconfigurable soft robots built from liquid gallium and neodymium iron boron microparticles, work that began years ago and has only accelerated since. Beihang University has partnered with Tsinghua Shenzhen International Graduate School on liquid metal alloy processing, backed by joint funding from regional science and technology programs specifically created to support this exact class of materials research. American researchers at Carnegie Mellon University previously helped identify the specific gallium-indium ratio now used across multiple labs, a detail that keeps this research collaborative rather than purely competitive. And publishers including Science China and the journal Device have fast-tracked peer review on liquid metal robotics papers throughout 2026. A sign editors see urgency most academic fields simply do not receive. China's National Strategy for Advanced Manufacturing has specifically flagged flexible and reconfigurable robotics as a priority research area, accelerating grant approval timelines for labs working in this space. In any market where a single material can replace an entire category of rigid, motor-driven components at a fraction of the mechanical complexity, a real cost advantage is not a trend. It is a competitive pressure no serious manufacturing company can afford to ignore. Here is the detail that puts the whole race into perspective. This is not a single company racing to patent one product. It is dozens of institutions across multiple countries racing to understand one material, because whoever controls the fundamental science tends to control every product built on top of it for a decade or more. Much of the underlying research remains published in open access engineering and materials science journals, letting scientists anywhere audit the methodology and data rather than relying on press releases. That transparency is unusual for a technology this commercially significant, and it is part of why the claims have held up under outside scrutiny. The material had already proven itself. The obstacles standing between a lab result and a global standard, though, were about to get considerably more complicated. If shape-shifting liquid metal robotics scales the way researchers project, industry analysts estimate it could touch a meaningful share of the roughly $40 billion global inspection and disaster response robotics market within the next decade, a market currently about the size of Iceland's entire annual economic output. Picture that entire market, every dollar of it, and imagine even a modest slice shifting toward machines that need no rigid joints at all. A secondary benefit comes bundled with that scale. Because liquid metal components replace dozens of rigid mechanical parts with a single reconfigurable material. Manufacturing waste and rare earth motor demand both drop substantially, with early estimates suggesting a reduction in per-unit rare earth magnet content of up to 30% in comparable designs. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. First, the load limit remains real. 2 pounds per square inch will not satisfy every industrial application, and stronger formulations remain years away from field testing. Second, gallium is not scarce, but refining it to the purity these applications require adds real cost, currently running several times higher than standard industrial gallium. Third, long-term safety data on repeated human body exposure for the surgical applications is still limited to a handful of published trials. Fourth, standardized certification for shape-shifting robotics does not yet exist in most countries, meaning regulatory approval could take years longer than the technology itself. Fifth, manufacturing at scale requires precision magnetic particle embedding that current factories are not yet equipped to perform reliably outside a handful of specialized labs. Sixth, cold climates below freezing risk, pushing some formulations toward their solid state permanently, a problem researchers have only begun to address. Here is the part that matters most in all of this. None of these 6 obstacles are secret, hidden in a press release nobody expects viewers to read. Every one of them is documented in the same published open access research that revealed the breakthrough itself, sitting in plain sight for anyone willing to look past the headline. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed robotics demands is a different question entirely. The story of liquid metal robotics is ultimately the story of what human civilization can build and where it can build it. Rigid robotics required expensive factories, precision tooling, and specialized supply chains that concentrated advanced automation in a handful of wealthy countries. A material that can be produced with existing microfabrication equipment lowers that barrier considerably. That matters most for the places that currently have the least access to advanced robotics. Disaster response teams in earthquake-prone regions of South Asia, pipeline inspectors across rural stretches of Africa and Latin America, and rural clinics that cannot afford a fully equipped surgical robotics suite could all benefit from a technology that does not require the same capital investment. Rigid robotics has always demanded. The access gap is real today, and closing it will depend on costs coming down faster than adoption in wealthier markets pulls resources away from it. What is genuinely new here, not incrementally better, but categorically different, is a robot that carries no fixed shape at all. One that can be solid enough to work and liquid enough to escape, on command, using nothing but a voltage or a magnetic field. That is not a minor improvement over motors and gears. It is a different category of solution entirely. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed robotics demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Technologies that change the fundamental geometry of what a machine can be do not stay contained to one industry for long. A material that can navigate space, rigid robots, cannot touch as disaster response, medicine, deep infrastructure, and eventually consumer devices, and small shifts in a foundational material tend to compound across every industry built on top of it for decades. If a machine that changes its own shape raises a question about what else might replace the rigid technology we have trusted for generations, that story is worth understanding too, and it is the subject of our next video. China's hydrogen plane just made every jet engine on Earth obsolete. The link is in the description. If this changed how you think about what a robot even is, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every 2 weeks. Now I want to hear from you in the comments. Would you trust a shape-shifting liquid metal robot inside your own body during surgery? Or does that idea cross a line rigid tools never did?